Hello everyone, this is Josef Nat here, and in this video I'm going to talk about turbulence modeling in transient simulations. This is a cooperation with Gavin Tabor from the University of Exeter. Here you see the finished results, the velocity magnitude and the kinematic subgrid scale viscosity, and by the end of this tutorial I want you to understand what this subgrid scale viscosity is. The goals of this tutorial are the following. I want you to understand turbulence, or at least have a slight grasp on turbulence. And I want you to understand the difference between Reynolds average Navier-Stokes equations and large eddy simulations, between these two modeling possibilities. I'm going to show you the case setup and the initial values and the boundary conditions. I'm going to run three transient simulations of a backward facing step, which is a two-dimensional simulation, and I'm going to use three models: the standard K epsilon model, which is a Reynolds averaged model, and the Smagorinsky-Lilly model, and a one equation model, which are large eddy models. The geometry is the same as in the last tutorial for the steady state simulations. On the left hand side we have an inlet with a width of 6 centimeters, and on the right hand side we have an outlet with a width of 9 centimeters, and in between we have a step, and we will set the velocity on the inlet, so we have a Reynolds number of approximately 44,000, so we have a fully turbulent flow. For that we will use the Pisoform solver, which is a transient solver for incompressible flow. At least this is the official description. So it is incompressible, it is transient, it works for laminar and turbulent flows, it is a single phase solver, and it is an isothermal solver. Now, regarding the equations that are being solved, incompressibility means that the continuity equation reduces to this simple equation where the divergence of the velocity is zero. In the momentum equations you can divide by the density, by the constant density, and with what you end up with is this pressure gradient term with the density, and in the diffusion term you have the kinematic viscosity instead of the dynamic viscosity. And also in this solver, if we are talking about P, the value P is not the pressure in Pascal, but is the pressure divided by density. Transient means that if in the solver it says that time equals, this time it really is a physical time rather than an iteration number as it was in simple form in the previous tutorial, and we have partial time derivatives in the transport equations. Laminar and turbulent means that we can solve the equations for the laminar flow, and there is also a possibility to add terms for turbulence modeling. Single phase means that there are no additional equations for multi-phase phenomena, for example, and there is no energy equation. And also in this case, the continuity equation and the momentum equations are not solved separately, but are combined into the Piso loop. Now let's come to turbulence. In the previous tutorial I talked about turbulence and turbulence modeling. To recap, turbulence is the chaotic change of field values like velocity and pressure in space and time. You will find turbulence in flows with low momentum diffusion and high momentum convection, and in the last tutorial I showed you this schematic sketch of the velocity u at a given point in space. If you measure the velocity at a given point in space, then I told you that we will have in a steady state flow a constant velocity, and the velocity will oscillate around this constant value. And these oscillations are time dependent, and the constant value is of course constant. And in the Reynolds average Navier-Stokes equations, we say that we do not care about these oscillations and we are neglecting those oscillations, but you make an error with that. So instead of considering these oscillations, we have to add something else, and this something else is this turbulent viscosity, which is a model viscosity, which has nothing to do with physical viscosity. It just models the transport and dissipation of energy neglected by setting this value to 0. And in the equations we use an effective viscosity instead of the physical viscosity, which is the sum of your physical viscosity and your turbulent viscosity. And the question is, how do you calculate this turbulent viscosity? And I showed you these values for the K epsilon model and the K omega model in the previous tutorial. I will show you this for the K epsilon model here because I'm going to use this model in the simulation. So in order to calculate the turbulent viscosity, here you introduce two additional quantities additionally to P and U. One is K, the turbulent kinetic energy, and the second one is epsilon, which is the turbulent dissipation. And you calculate this turbulent viscosity with a constant value 0.09, then you multiply it with K squared divided by epsilon. And important is that you have an additional equation, a transport equation for K, and one transport equation for epsilon. In large eddy simulations, you do not set these oscillations to 0, all of them, but what you are actually doing, you are making a low-pass filter. You are resolving the large scales, the scales that you depict with your grid. You assume that you are resolving those scales, and you are modeling all the small scales that you do not resolve with your grid. And you are filtering with a given filter function, and there is a cutoff length scale delta and a cutoff time scale. And above this length scale, for example, you are depicting the oscillations, and below this length scale you are modeling it. Very similar to the Reynolds average Navier-Stokes equations, but there you are modeling all the oscillations, but here you are depicting parts of these oscillations and you are modeling parts of it. Now, and also in this case, very similar to the RAS models, we are using an effective viscosity, which is the sum of the physical viscosity and a model viscosity, which is called in this case subgrid scale viscosity. And the question is, how do you calculate that? And in most of the LAS simulations, it is given by a constant value of 0.094 multiplied by delta and multiplied by the square root of K of this turbulent kinetic energy that you saw also in the standard K epsilon model. And this delta is mostly calculated, and this is what we will do also in the simulations. It is calculated by taking the volume of your cells and then taking the cube root of the volume of each cell. Since we are doing a two-dimensional simulation, this is a little bit different for two-dimensional simulations, but in 3D you are actually taking the cube root of your cell volumes. Now in the Smagorinsky-Lilly model, our first model, we are calculating the turbulent kinetic energy out of the velocity field. So you are creating the grad U tensor, then you're taking the symmetric part of it and the deviatory part, then you calculate the magnitude and you square it, then you multiply this value with your delta. This is the same delta as here, delta squared, and then you multiply a couple of constants on it. And this is how you calculate in this model K. This is a very simple model, and then you take this K value, and then from this value you calculate your subgrid scale viscosity. Important is that there is no additional transport equation. So you do not transport K, but rather instead you calculate it out of your velocity field. In the one equation model, which is called one equation eddy in OpenFOAM, you have this K value, but in this case you have a transport equation for K, with a convection term, a diffusion term, source terms, and also in this case you have a partial time derivative. And so In the Smagorinsky-Lily model, we don't have to specify a k value in the 0 folder for the initial values and the boundary conditions, but in the one equation Eddy model, we will have to set a k value. Again, and this is what the geometry looks like. I'm going to go to the source code of PiezoFoam. Incompressible, then PiezoFoam. And PiezoFoam, it is very similar to SimpleFoam. You have the header, a couple of header files are included, the time is created, mesh is created, and the fields are created. Which means that your P field is taken from 0 or the latest time step. P is again pressure divided by density. Then your U field is taken, and then your phi value is created. And again, if it is present in your latest time step, then it is just taken from there. If phi is not in your latest time step, like in 0, as you will see, then it is calculated out of the velocity field. Then we enter a while loop, which is now an actual time looping. And if it says here time equals, it is not an iteration number as it was in SimpleFoam, but this is a physical time. And then you will find a Courant number where the solvers can set your time step according to the Courant number. And if you do not know what the CFL or the Courant number is, check it online or in a book, or check it in my CFD basics tutorial. I'm talking about this value in the grid convergence tutorial. Okay, but then a vector matrix is set up where you find the partial time derivative of the velocity, and if I go back to the Navier-Stokes equations here, this is this partial time derivative, then the divergence term, which is this term, the convection term, and then we have this div-def-ref term, very similar to SimpleFoam, which is the fusion term and the turbulent terms. And then we are solving this vector matrix with the pressure gradient term. And actually here we are solving the momentum equations at this point. Then we are entering two for loops, an outer loop and an inner loop, with n correctors and n non-orthogonal correctors. And in the inner loop we are solving the pressure equation. And if we're finished with this looping, then we are updating our velocity with the new pressure values, and then we can do an additional outer loops. So then we again solve the pressure equation a couple of times, and then we are updating the velocity. And if we say that we did enough outer loops, then we calculate the turbulent values, and then we go to the next time step. Okay, this is what the source code looks like, and as you see, turbulence enters at this point, and this div-def-ref is very similar to the div-def-ref term in SimpleFoam. So I will not talk about the turbulence models. You can check them in SRC turbulence models if you want. But actually what I want to do, I want to open up a terminal and set up the base case. For that I will go into the tutorial folder of PiezoFoam, and here you have three folders: laminar, LAS and RAS simulations for laminar cases, large eddy cases and Reynolds average cases. I will just go into LAS, and here I'm going to do 3 simulations, and I will do also the one RAS case here in this folder. Okay. Now I'm going to set out the base case. For that I will just copy the base case from SimpleFoam because the geometry is the same as before in the previous tutorial, and I want to mention that the grid is way too coarse for an actual LAS simulation, so keep that in mind. But I will use this coarse mesh so the simulation runs in approximately 90 seconds or 100 seconds. I do not want to run simulations for hours or days here. But you have to keep in mind that for your actual thesis, if you want to do LES simulation, you have to take care of the refinement of your grid. So keep this in mind. But I will just copy the base case from SimpleFoam. If you do not have this, then go check my previous tutorial on SimpleFoam and steady-state turbulence modeling and then set up the case. It's the second video, the second part of the tutorial. I will just copy it here. Now I have it here. I will enter. And I'm going to set up the case so I can use this base case both for the K-epsilon model and for the two LES simulations. But let's compare. We set this up for RIS models, but I want to compare which values we need for LES simulations. So I will go into the same PisoFoam folder, LES, and there is this PITS daily tutorial which is very similar to our case. So I will just go into PITS daily. And let's take a look at what we have here and here. So what do we need for LES simulations? So in 0 for the RIS simulations we needed, at least for the K-epsilon model, we needed epsilon, K and nu T additionally to P and U. And here, as you see, for LES simulations we need K, nu SGS, which is the subgrid scale viscosity, and nu tilde, but we will not need this for the two models that we want. So what we need is K and nu SGS. In constant, we need LES properties rather than RIS properties, and we need this turbulence properties dictionary. And we have control dict FV schemes and FV solution in both cases, so we have to do slight changes here. And let's start in 0. So we need K and epsilon for the K-epsilon model, but for the LES cases we need K and nu SGS. So let's take a look at those. So I will open up K, and also here the RIS K. So we fixed the value on the inlet. The same is being done for the LES simulations. I'm going to use zero gradient instead of inlet outlet on the outlet, but in the RIS simulations we used wall functions. If you do not know what wall functions are, I pulled up the Wikipedia page here, and please check the last tutorial on wall functions. I'm talking a little bit about wall functions. And we are not using wall functions in the LES simulations, but rather we are fixing the value of K to 0. So here what we are actually assuming that we are depicting the viscous sublayer, and since we are using no slip boundary conditions for the velocity, also the oscillations are 0, and with that the turbulent kinetic energy is 0. So, and again, for that our mesh is way too coarse, but if you are doing an actual LES simulations with a correct grid refinement, then hopefully you can make this assumption. So I will just type here fixed value and 0, and the same for the lower wall. And 0, and now I will save this, but not as K, but as LES. Yes, save under different name. Yes, why? And now I exit this. So we have now in 0 we have an epsilon and a K, which is the RIS K, and we have a K value for LES simulations. Now we need a new SGS, which looks like this. You have 0 gradient everywhere, and we initialize the value with 0. So I will just make a copy of the new T value and call it new SGS. And if I open it up, then I have to change a couple of things, and I will just delete a couple of lines, and then use just 0 gradient everywhere. Very good. So now we have all the values that we need. We have epsilon and k for the k epsilon model and nu t. We have an LES-K value and a new SGS, and we have our P and U, so we set up the 0 folder here. Let's go into constant. Okay, so we have an arrays properties for the k epsilon case. We have the transfer properties for the physical viscosity, which we set to be 10 to the power of -5 in the previous tutorial, and we will use this value. But we need these LAS properties and the turbulence properties, which I will just copy from this PitzDaily folder. Turbulence properties and LAS properties. Now we have those here, and in turbulence properties it says that we want to use LAS models, which is true in 2 cases, but in the k epsilon case we want to use actually an arrays model, so we have to uncomment the LAS model for the k epsilon model. Okay, so now in LAS properties, in the PitzDaily tutorial they use the one equation eddy model, which we will use, but we will also want to use the Smagorinsky model. And if I want to use Smagorinsky, I will just delete one equation eddy. And here you see this delta value here. This is where you set that you want to calculate this delta with the cube root of the volume of your cell. Okay? So this is how this works, where you set it. And now I want to save this and go into System, and in Control Dict we are using piezofoam. Latest time step is good enough, start at 0, end time, and we now have an actual physical time, not an iteration number. So we do not want to simulate 2000 seconds. I want to simulate 0.2 seconds, and again, delta t is not an iteration number, but actually a physical time step. So I know that 5e-5 works, and I want to save after 100 time steps. So after 5 milliseconds, 10, 15, and 20, and so on. So I will save this. In FV schemes we have to set this value from steady state to Euler. And as for the divergence schemes, we do not need the R entry, because we are not using in this case Reynolds stress models, and we do not need the nu tilde. We need k and epsilon for the k epsilon model, for the 2 transport equation within the k epsilon model, and we will need for the 1 equation eddy model the k entry. So I will save this, and in FV solution we need here an entry for P final. And since we are not using the simple algorithm but the piezo algorithm, I have to change this. And again, if you remember back, here in the source code we have a non-orthogonal corrector entry and an end corrector and a non-orthogonal corrector. So 2 loops, inner and outer loop, and this is the inner loop, the number of additional inner loop. We always solve the pressure equation at least once, and this value is the number of additional iterations for the inner loop, and n correctors, this is the number of outer iterations. So we will do 2 outer iterations and only 1 inner iteration for the pressure equations. Okay, I will save this. Now I finished the case setup. I will just make copies of this base case and call them k epsilon, then Smago, and one egg added. Enter. Now I will just close this window, and now we have base case and the three cases with k epsilon, one equation at the end for the Smagorinsky model. Okay, but before I start with the simulations, I would like to stop recording now. I hope that you enjoyed the first part of this tutorial and that you learned something. I would like to thank you for watching, and I hope to see you in the second part of the tutorial.